if we looked at to determine what substitution mechanism the following substrates would undergo, that kind of question is asking you to look back at that chart. Okay? It's saying, okay, here are a variety of substrates. Which ones are going to push under which mechanism? So if you know the SN2 is dependent on steric hindrance and wants to get away from sterics, i.e. you're advancing your zero area or primary halides, when you see that substrate, you immediately think an SN2 reaction. Okay? If you look at your substrate and it's tertiary or secondary, that works for an SN1 because we get a more stable cation. Okay? So the idea is to look at each of the individual pieces and say, okay, what things match where? Okay, so the substrate one's the biggest one you could see. We could also go through and look at ranking nucleophilicity. So I changed this question around a little bit. Instead of saying a direct rank, we did comparing the following pairs. Okay, so what I could ask you to do is say, given hydroxide, that was really ugly. Let me try that again. If we had hydroxide with all those electrons around it versus a carbanion, okay, something along these lines. And I asked you to tell me which of those is the most nucleophilic. Okay? To do that, you'd have to be familiar with all your rules. So we could go back and say, okay, what made something nucleophilic? Has to have donatable electrons. It has to be negatively charged. Both of those species were negatively charged. Okay? Nucleophilicity decreases from left to right. Lower electronegativity means more nucleophilic, which means of those two species, which have now deleted themselves, thankfully, that was nice, we had our hydroxide versus our CH3. They're both negatively charged. We move on to Rule 3. Rule 3 says electronegativity. Which of those is the stronger nucleophile?
CH3.
The CH3. Okay? So the idea is to go through and treat each pair, even if it's a ranking system, find a pair, rank those two. Then take one more and compare it to one of those that you just ranked. And slowly start to build a complete ranking system. So go by pairs all the way through it. The examples that I gave you before were problematic because what I ended up doing was picking a wide spectrum of possible things to rank, not picking one consistent trend. I ended up picking like 3 or 4 different trends, which makes it difficult to rank. Okay, so if we went and looked at the, what are we looking at now? The leaving group ability. If we look at water, H2O versus ammonia, which of those is the better leaving group? Okay, well, leaving group was the opposite of nucleophilicity. We want our leaving group to hold charge or hold the electrons. So both of these took electrons. Okay, we can see that with the lone pair, okay, when they left. Which of those is better able to hold those electrons? H2O, why? More electronegative. So you remember way back when I said you need to know your trends in electronegativity. You need to know what different bonds are and the different polarities and the different interactions that you can get out of those. It's because all of those interactions dictate the reactivity that you're seeing here. So if you're familiar with those, you can start to build your trends. Okay, so we end up saying water is our better leaving group. Okay, because it can hold that charge better. Yes?
Would you just give us the water, ammonia, chloride, iodide?
So yeah, I would give it to you. As far as this goes, what I tried to do is now put these in pairs that made sense. So ranking chloride versus iodide. I wouldn't give you the names. The name, that's why those are small, is those were for my notes. I didn't have time to draw on the structures.
Okay, perfect. Thank you.
Yep.
But you would?
I would give you structures on the exam. Yeah. I don't expect you to have the names for all of those. Okay. I skipped over this one, the bromobenzene, as far as which substitution mechanism. So let's go ahead and take a look at that now that we've got a little bit more time. So bromobenzene, this is the structure of benzene. If we add a bromine to that, that's a B. It just got worse. We'd have bromobenzene. Okay, what kind of halide do we have? What kind of substrate? Where's the halogen attached? It's attached to this carbon. Okay, according to our classification systems, we then say, how many carbons is this one attached to? 2. So we could start to call it secondary. which would be obnoxious because secondary means SN1 or SN2, so that's not particularly helpful. However, is it the same kind of classification that we've been looking at before? Everything that I put up on the slides before, we were looking at alkanes, okay? No double bonds. We now have a double bond. Do double bonds change the chemistry of the molecule? Yes, which means we do not classify this as primary, secondary, or tertiary. What do we end up classifying it by? Any guesses? Begins with an H. The hybridization of that carbon. Okay? You'll notice that wasn't part of any of the trends that we've looked at so far. So let's evaluate our individual pieces. For the SN2, what did we say has to happen? What are we concerned about in the SN2? Primary concern was sterics or steric hindrance or size. The backside of that carbon-bromine bond has to be accessible. What do you think about the backside of this carbon-bromine bond? What do you see back there? What does this line represent? Electrons. What does this line represent? What does this line represent? Electrons. What are the odds that I'm going to be able to take a nucleophile, which is going to have what charge? Likely a negative, and be able to jam that in the backside of that bond?
Very low.
Very, very, very low. Would this substrate be expected to go in an SN2 type reaction? No, because it doesn't have an accessible backside. Okay? So this species is very unreactive in an SN2 type reaction. So we could try the SN1. What happens in the SN1 reaction? Okay, we need that. Our alkyl halide here, there's our halogen and there's our alkyl portion. Okay? If we give that enough time and say energy, what ends up happening? Particularly if we don't give it a nucleophile. Eventually what could potentially occur is that we end up losing a hydrogen ion and the halogen, and we end up forming a double bond. Okay? The net result is that we lost HX. Okay? If we combined HX, positive and a negative, we'd end up with what kind of a charge structure? It would be neutral. Most compound or most structures that we refer to as being neutral we'll call molecules. So in the process of an elimination reaction, we're eliminating a small molecule from a larger molecule. Okay? So it's then taking a look at those, or that overall reaction, and trying to decide how did that occur. So we go through and evaluate what bonds were broken and what bonds were formed. Okay? And in the case of this reaction, what I ended up drawing up before was a resonance structure for a carbon-carbon double bond. We could see that structure something along these lines, a positive and a negative. Well, if our halogen leaves, what does it leave on the carbon? A positive charge. It's lost electrons. What happens if H plus leaves? What happens to the electrons in that bond? It stays, giving us the negative, which is the exact same as a double bond. Okay? So we're evaluating ultimately a resonance structure. Yes, our final answer looks a little bit different, okay? And it may become hidden as far as an answer goes, but that's exactly what we're looking at. We're looking at that positive negative. The only thing that's really happened is we've broken the hydrogen and the halogen bond. Okay? So what we'll do is evaluate those two bonds as far as how the reaction could occur. So when we looked at the unimolecular reaction, okay, what we could go through and do is evaluate based on our carbon X bond breaking first. So if we looked at this structure and we wanted to say we break the carbon hydrogen or carbon halogen bond first, how could we do that? How would we show that?
Arrow from the electron group.
What electron group? Right idea?
C to X. No.
You can be, no, you're right, but
Yes.
I don't quite like electron group. There's a better way to refer to it.
Electron.
The what, though? What would you represent?
Air.
The
Arrow.
bond.
Come on. It's an arrow.
It's an arrow coming from the bond to the halogen. Okay? So what we're saying is that happened in one step. So we'll go ahead and now show out our product of that. what do we end up forming on that carbon? A positive charge. And we end up with our halogen with a negative. Come on, where's my negative? Okay. This step should look really, really familiar. It looks an awful lot like the very first step of the SN1 reaction. Okay? So the first step here, so what we've seen before, is if we had a nucleophile, okay, with some electrons, is that nucleophile could then share its electrons with our carbon. And we could get our substitution reaction, right? We ended up with our nucleophile on there. Hydrogen didn't change, nothing else changed, right? And in that case, we followed an SN1 reaction. 1, because we formed our cation, N, because we got the nucleophile, and the result is that I substituted my halogen X for a nucleophile. Okay? But we started this whole discussion off by saying we don't have a nucleophile. So if there's no nucleophile present, we now have to evaluate the structure and say, is there something else that we could do? Okay? What's the problem with that initial structure to begin with?
It's unstable.
Why is it unstable? Good answer.
Because it has a charge.
Because it has a charge. It's got a positive charge. How do I stabilize a positive charge?
Add electrons.
Just like I did here, I could add an outside species, except we're saying we don't have the outside species, which means we have to find electrons from within the structure. Okay? Where's the easiest source to find electrons? From the bonds. We could pick bonds immediately next to the carbon, but if we took the electrons out of that bond, what happens? Sure, this gains electrons.
Then it's not together, it's two separate.
There's no bond there. This one gained electrons, and we form a very odd species referred to as a carbene. What happened to this carbon? Lost electrons becoming cation. Did we do anything productive? We just made two more reactive species. So it doesn't make sense to address the bonds immediately attached to the carbon. So what we'll do is move one atom further away and address those bonds. Which of those bonds are willing to give up electrons? Okay? And that's where we look to that hydrogen. We'll take the electrons away from that bond, our carbon-hydrogen bond, and we'll shift them into a double bond. What's the result of that? Well, we've still got our carbon backbone. We didn't touch those other bonds out there. Okay? We moved electrons from that from our hydrogen bond into the middle, which means how many electrons do we have in between those two atoms? 4. Every line is 2 electrons, so we need another line, also known as a double bond. What else is floating around? We've got H+, and we have our halogen. Okay? And what we've done is now an elimination. We've lost a small molecule if we combined those two. Okay? We've already addressed one of our biggest concerns with this, or what will be one of your biggest concerns, and that is that this looks very, very similar to the SN1 mechanism. Okay? The slowest step of our elimination reaction is forming the cation, which is the exact same step as forming our SN1. Okay? Which means if I have an SN1 reaction, more than likely I'm also going to have an E1 reaction happening at the exact same time. So I want to be able to control which one predominates.
What do you mean by E1?
An elimination reaction, unimolecular.
Oh.
Because in our rate limiting step, how many species are involved? 1, unimolecular. Okay? So, deciding how we could control these. What does the SN1 reaction need to work? The SN1 reaction. It needs to have a nucleophile. So how could we potentially favor one reaction over the other? I could make sure that I've got a nucleophile. Okay? If I wanted the elimination reaction to occur, what might I try and prevent being in there? I want to make sure I don't have a nucleophile. Okay? The handwriting is not the greatest. That's close enough, right? Okay? The other things that we want to do is realize where our big change is. So we said nucleophile, great for our SN1, but what else is happening in our elimination? What's the next critical step of the elimination? What's happening in our second step? We have to break the CH bond. Okay? So if I want to push the elimination, I need to favor the breaking of that bond as best I can. Okay? What's the easiest way to break bonds? We can add heat. So one of our big things that we'll see, particularly for an E1 elimination, would be heat. Heat's going to help drive our elimination reaction. Even if we do get the substitution, they're all reversible reactions, and we can end up pushing and forming our elimination product. Okay? Questions about that one? Okay. What happens if we now change the mechanism and we move to a different style? So in this case, now we'll look at the bimolecular reaction. Okay, which means E2. Okay, and in the E2 reaction, everything happens all at once. Okay, so we'll go through, we'll break the carbon X bond. How can we break that bond? From the bond to our halogen. We also need to break or form our carbon-hydrogen or carbon-carbon double bond. How do we make that? An arrow from the bond between the hydrogen and the carbon to the bond between the carbon and the carbon. Okay? And the result is what? Okay? With our H plus and our X minus. Okay? So we've now done everything in one step, which should kind of ring some bells. Like perhaps the same kind of idea that happened in the SN2. Okay? So the E2 ends up being very similar to the SN2 as far as the effects and what things are going to control it to a certain extent. Okay? Again, we have this carbon-hydrogen bond. Okay? And we need to break that bond before this reaction can occur. So what things might we add to this to help the reaction along? So heat works. I think I heard someone say heat, but I may have made that up. Okay, so heat is a possibility. The other big one would be a base. What characteristic of a base is going to help us out here?
An electron donor?
Kind of close. We're having our alkane, our alkyl halide, act as what kind of a species? What did it do? It donated what? A proton, making it a Bronsted-Lowry acid. How can we react, or what should we react a Bronsted-Lowry acid with? A Bronsted-Lowry base, which will be a proton acceptor. How can it accept protons? What does it need to have? It needs to have an electron pair. So it does come back to your electron donor idea, but it's better referred to as a Bronsted-Lowry base, not looking at the electron donor. How is that going to change our mechanism? The base needs to take that hydrogen. So how can I show the base taking that hydrogen? I can draw, whoa, what was that? Sorry, it was doing something weird. I'm going to draw my arrow starting from my source of electrons, my base, and moving it towards the hydrogen. How does that change my products now? Now I'm going to have H base. My base will be positive now because it's accepted. It started neutral here. Okay. And we can now facilitate and make this reaction go a lot faster. Okay. So that's something that we could do for the bimolecular reaction. If we can make sure to push the SN or the elimination reaction, or E2 reaction, that we're going to make sure to add a strong base, because that base is going to react with that hydrogen and help us produce our double bond product. Okay? Anybody have any problems with bases? What was the other definition you came up with?
Electron donor.
It's an electron donor. If a base is an electron donor, so we're looking at it as a Bronsted-Lowry base, so it's an electron donor, right? What else could it act as? What other species are electron donors? Nucleophiles, which means when we add a base, we have to make careful that the base that we add is not nucleophilic. Because if it's nucleophilic, what happens? We're going to run in the SN2 reaction. Okay? Which is a very fine line to walk, because a Bronsted-Lowry base is effectively donating electrons. What is a nucleophile doing? Donating electrons. So the difference between a nucleophile and a base is very, very minute. It's not the easiest thing to control. Okay, and we'll talk about that, I think, in a few slides here. Okay. One more thing that I want to talk about with the E2 elimination. So when we looked at the SN1 and the SN2, we looked at stereochemistry and the effects, what you could see out of those. I know there's a lot of things up on this slide. The E2 elimination has very peculiar stereochemistry requirements. Okay? Just like the SN2, it has to have a backside attack. Your base has to come in and remove the hydrogen, okay, in such a fashion that the electrons in that bond, I'm not going to be able to draw on this, but let's see what I can do. In that bond, go to form the double bond between our two carbons, which would then force out the halogen. Okay? So the electrons from that bond breaking have to push out the halogen from the back side. It can't do it from the same side, because in the same side situation down here, where do those electrons come through? Whoa, where'd it go? There's our hydrogen. There are our electrons. Our electrons would have to go where? Stop copying. Towards the halogen. What's going to happen with our electrons when they get near the halogen? They're going to repel, because the halogen has a lot of electrons. Okay? So the complication with the E2 elimination is that we have to have the arrangement that's shown up here. Okay? This arrangement is critical for this mechanism to occur. What is the relationship between the hydrogen and the halogen in that arrangement, in that projection?
Anti?
They're anti to each other. So for an E2 elimination to occur, you absolutely must have the anti-configuration. Without that anti-configuration, you will not get the elimination product. Okay? So it's something else that we could add to our reaction, because we could put something in the way that prevents that anti-arrangement, which would mean what would be favored? The elimination or substitution now. Okay? Because we don't have the potential for our elimination.
What does that LG stand for?
LG stands for leaving group. Good question. Okay. Other questions about this slide? Okay, and we will do some examples that evaluate this. Okay. Now we get someone's fun name, Zaitsev's, which you might also see. I can't remember how your book spells his name. Whoops. Might see it spelled with an S. Zaitsev. You might also see it spelled something like that. I've also seen it, I think, with an I. Okay. You'll see, I have no idea. It's probably because he's Russian and nobody likes the Russians. I think it's a reasonable guess, right? Okay. Yeah, actually, it will go on YouTube. That'll be awesome. Maybe I'll edit that later. Yeah. Frowny face, yeah. There we go. So when we went through and looked at our previous mechanisms, we only saw one hydrogen and one halogen, one leaving group. Remember, I left hanging bonds out there. I didn't specify what those were. Okay? When we look at an individual carbon, though, how many hydrogens are typically attached? Only one or more than one? Usually more than one. Okay? So if we were going to look at this reaction, and let's insist that it's going to be an elimination reaction, okay, what mechanism, first off, do you think it's going to go by? Two ways to answer this. One, we could pretend you can't see this. What mechanism would it go based on? Where's our leaving group?
Bromine.
So it's a bromine. Where is it attached?
To a carbon.
To a carbon that has how many other carbons attached?
3.
3, making it tertiary, which would suggest which mechanism?
SN1. SN2.
Careful. What mechanisms are we looking at here? Elimination. So you're right with the 1, but not the SN. E1. How else could you figure out it was an elimination or an E1 reaction? We've got our cation in the intermediate. Okay, so we're looking at an E1 elimination in this case, but it applies both with the E1 and the E2. So if we go through and look at this, our bromine can leave, takes the electrons, and we form our cation. Okay? And we looked at our reactions before. We looked to the atom immediately next door to our cation, because we said the bonds weren't or didn't have available electrons or reasonable electrons to take. So we looked to the atom next door and looked to see if that atom had something bound to it that we could take electrons from. And what we were looking for is a hydrogen. So if we go through and take a look at those 3 options, all 3 of those options have at least 1 hydrogen on them, which means we end up with how many possible products? We should end up with 3 possible products. Let's see if I can number this accurately. Call this 1, 2, 3. What would your product look like if it was number 1? We take the electrons away from that hydrogen to form our double bond there, and we end up with our ring. We didn't do anything to that carbon. There's our double bond, and there's that methyl. Everybody see that? Okay. What happens if we did carbon 2? I'm going to run out of space, but I'm going to try it anyway. If we look at carbon 2, now where's our double bond going to show up? It's going to show up out there. Everybody see that? So what we've done is taken the electrons away from that hydrogen and formed our double bond. What happens in case 3? We're going to take our electrons from that hydrogen to form our double bond, and we end up with this product. Make sure I draw this right.
Could you go low with that instead of going to the, like you went up with the bond, could you go down? You pointed the green arrow up.
No,
Where did I point the arrow towards?
Oh, towards the cation.
Towards the cation. This is all about providing electrons to stabilize the cation. Okay? As far as moving it downwards, if we attempted to do that, we'd end up trying to form a double bond here, right? What happens to that carbon then? It would have 5 bonds. Can you do that? No. Okay? So all of these mechanisms, or each of these 3 products, are all about trying to stabilize the cation. Each of them are removing a hydrogen or losing a hydrogen ion, okay, towards our base, and we could even show the extra arrows from our base coming in to attack each of those hydrogens, okay, to generate these 3 possible products. Okay? Does that mean we get 3 equal products? And it turns out not. The only product that we really see in this case is product 1. We'll talk about that. Okay. So now the question becomes is why? Well, what's the difference between each of those 3 things, or 3 products? So where our double bond is located. Okay. What product do you think we would form? Something unstable or more stable? More stable. So let's evaluate the stability of the only thing that's different between these, the double bond. So let's take a look at the double bond here. What makes it reactive? What makes the double bond reactive? The double bond itself, your pi electrons, are reactive. For those to react, they have to come outside of the structure, right? Okay. What do they have to come outside around? What's near them? What did I just circle in there? Carbons, which have electrons. What happens when the double bond electrons try and go out? What do they encounter? More electrons, which means they panic and go right back to where they started. Okay. What happens if we say move to product 2? Well, oops, I ran out of space there. I can't quite draw them on there. So I'm just going to say they're there. Let's make it shorter. Let's see what I can do here. We've got 2 hydrogens out here, right? What's near that double bond? We've got 1, 2, 3, 4. Come on, draw. 4 things around that. What are those 4 things? 2 carbons and 2 hydrogens. Which is going to be easier for the electrons to get out? By the hydrogens or by the carbons? Why the hydrogens? Less electrons. So which of these 2 has a less reactive double bond? 1, because it has to fight through electrons to get out. Whereas 2 can go out through the hydrogens with relatively no resistance. Okay. What happens in case 3? And what's out here? We now evaluate in case 3. What do our electrons have to go out by? 2 carbons that way, or a carbon and a hydrogen. So if we compare 3 back to 2, which one is a more stable double bond? Which one can't get its electrons out? 3. Okay. Which one's more stable, 3 or 1? 1, because lots of electrons around it. Okay. So what we're doing is evaluating each of these intermediate products and trying to decide what makes them reactive, what makes them less reactive. If we had 3 equivalent energy products, we'd end up with 3 products. But our products aren't all the same energy. Okay? What we just described and evaluated, please be on the next slide, which apparently has animations. Painfully slow animations. Okay? Is the substitution patterns on a double bond. Okay? In our first case, we have a tetrasubstituted double bond. That double bond is the least reactive or the most stable because those electrons aren't able to leave the structure because the carbons are in the way. Okay? When we move to this case, we've got 3 carbons. We call it tri-substituted, but it still has 4 things attached to it, right? So why do we call it tri-substituted? Because one of them's hydrogen, and what's one of our primary rules with simplifications in organic chemistry? Nobody cares about hydrogen. Okay? So we've got tetrasubstituted, tri-substituted. We could move to di-substituted. Okay? Now we've got 2 methyls. Okay? We could move to monosubstituted. It's not on here, but what would be the most reactive? 0 substitutions. Okay? Now that double bond is extremely accessible. I added an extra structure here. Okay? In the di-substituted case, we've got 2 possible positions. Cis and trans. Why do you say cis and trans? Which one's cis? The top one. Why? They're on the same side, whereas on the bottom one, they are trans because they're on opposite sides of the double bond. Whoops, not that line. Okay. No, that was right. That was the right line. Sorry. They're on opposite sides of our double bond. Okay, whereas in the first case, they're on the same side of that double bond. Okay. There's actually another one which I didn't show on there. Okay. We could put those 2 methyl groups on the same side of that double bond. We could put them both on 1 carbon. Okay. It's not called trans in that case, but yes. Okay. So we've got all of those possible reactions. What does Zaytsev's rule say? Says That's why we don't like the Russians. We can't talk after we say their names. Dang it, I did it again. Your major product in an elimination reaction, and for that matter, all reactions, is going to be the more substituted double bond. Why the more substituted? Because the more substituted is the more stable. Everything pushes towards stability. Okay? And just because this Russian guy happened to come up with it in the elimination reaction, we now have to forever remember his name as saying the exact same thing we've told you from day one. We're always forming the most stable product. In this case, the more substituted.
Why do they call it that? The most substituted.
Because it just has more substituents on it. Non-hydrogen substituents. I don't have a better answer than that. Sorry. Okay? You'll notice if you look really, really carefully, I do have a little note down here saying exception. Okay? There is an exception to this rule. You can end up generating what's called the Hoffman product. Of course, the guy that found the exception to the rule gets his name attached to his own rule. Okay? The Hoffman product is looking only for the E2 eliminations, because it's the only case where we can generate enough energetics to force this to occur. You can end up forming the less substituted double bond if the halide that you're using is extremely sterically hindered. So we're looking at a tertiary halogen. So in this case, we've got that cyclohexane, and if you zoom in or look real carefully at that bromine, the carbon that bromine's attached to has how many carbons attached to it? 3, so it's tertiary. Okay, so if we have that and our second part of that rule, we have to have a sterically hindered base. What does sterically hindered mean? It's big. Okay, there's things in the way. The classic example of a sterically hindered base is this guy, T-butoxide, okay, or tert butoxide, tert butyl oxide. Okay, so only in those circumstances might you see what's referred to as the Hoffman product. It's less substituted. It's fairly rare. I don't think I'll test you on it, but we might throw an extra credit question in there. Okay, along those lines. Okay. Questions about that? Okay, so mechanisms. Now trying to decide between when we're given an individual substrate, we're told it's an elimination, trying to decide which mechanism do we have. Do we have the E1 or the E2? Okay? You'll notice in the E1 that your rules look very, very similar. Okay? For the E1, we want tertiary and secondary. Okay? Why would we want those? It's the very first thing formed in an E1 elimination. A cation. Stable cation. Okay? Pretty much the same rule as our SN1 reaction. Okay? We'll typically use heat. The heat's there to help break that carbon-hydrogen bond as best we can. Okay? We typically won't use a base. Okay? So the base strength is usually unimportant. Why is the base unimportant? Well, when is that bond broken? After we form our unstable intermediate. After we form that cation. Okay? So we don't typically care about the base. We're going to end up using a polar protic solvent. Why would we want the polar protic solvent? What does the polar protic solvent stabilize? Stabilizes our cation. Okay? Just like in the SN1. Okay? We haven't talked about rates, and I really don't want to get into that, so we'll cross that guy out too. You'll get the Zaitsev's product with these, so you'll form your most substituted double bond. And then no special geometry or stereochemistry limitations are going to be involved in this. Okay? If we move to the E2, okay, you'll notice that in this case, we say tertiary reacts the fastest. But didn't I say that E1 and the E2 are related to SN1 and SN2? And in the SN2 case, we said which one reacts the fastest? Our zero area, our primary. We're seeing the reverse order here. Why are we seeing the reverse order? Because of the Zaitsev's rule. We're trying to form the most substituted double bond. The more substituted double bond is going to form on a tertiary halogen or a tertiary halide. Okay? So our Zaitsev product or our Zaitsev rule is what's going to determine our reactivity. And we end up seeing tertiaries react faster than secondaries, faster than primaries. Okay? And it's due to that substitution. It's the stability of our product at the end of this. Okay? One of the big requirements for the E2, which is similar to the SN2, we need a strong base. Okay? In the SN2, we needed a strong nucleophile. In the E2, we're looking at its equivalent. It's a strong base now. Okay? The solvent is not particularly important in this case, usually because in most cases to get that strong base in there, you're in a protic solvent anyway, but you've added a whole bunch of base to neutralize it. Okay? So you don't have to stress about solvent dependence in the E2. Okay? We've got our rate again showing up. We can or will primarily get the Zaitsev's product, but we might see the Hoffman show up as a secondary consideration. And as far as the geometry goes, we absolutely have to have that hydrogen leaving group anti-relationship. If we don't have that relationship, we can't get the E2 elimination. Okay? At least as far as you're concerned. Questions about that? Okay, so let's play around with some problems here. We'll take a look at cyclohexanes, everybody's favorite. Okay? You'll notice there's also some wedges and dashes, which means even further everybody's favorite, we're going to have to deal with stereochemistry. Okay? What mechanism do you think we're going to see these elimination reactions occur by? So we could look at our substrate. Where's our halogen attached? Got it attached to it. Whoops, wrong button. We've got it attached to our carbon. That carbon is attached to how many other carbons? 2, meaning that our halogen is secondary. Okay? Secondary could favor pretty much anything, so that's not particularly helpful. So we'll push away from our substrate and look at our other reagent. What's our other reagent? A strong base, which means E2 elimination. Okay? So everything needs to happen at once. And as soon as we see that, what does that mean? Our geometry is going to be critical to this reaction. Did I spell that right?
Sure.
Geometry. I think that's right, isn't it? That looks pretty good. It's a silent P, right? So, if we go through and evaluate our elimination, okay, we'll have to find our leaving group. So we already know where our leaving group is. That usually stands out. Where's our leaving group?
Bromine.
Bromine. So the bromine will likely take our electrons. Okay. Since it's an E2 elimination, we have to supply electrons to help stabilize the carbon as the bromine leaves. Where do we find those electrons?
The strong base.
No. We're going to have to find a bond to supply those electrons. What bond do we look for? A hydrogen bond. So we'll go through and evaluate where our hydrogens are. So we'll look to the atoms next door. Which of those atoms has a hydrogen? They both do. Which one do I take the electrons from? Okay. We would say we could go from here, which would be product 1. What would our product look like in that case? The bottom one? Yeah. No. Okay, what would our product look like in that case? There's our double bond. Okay, that would be, we'll call that, I guess, A. If we look at B, what's our product for B if we pulled that hydrogen off? Everybody see that? Which one is favored? A. Why would A be favored? More substitution. We would expect A to be our product. However, in that process, did I evaluate anything to do with the geometry? No. Which means we're going to have to reevaluate this and make sure we look at our geometry before we decide what our product is. Okay? I know you guys aren't going to like this. I had to draw 2 cyclohexanes up there because I don't remember which one gives you the Hoffman product. Okay? So how can we see geometry on a flat structure? Okay, we could go with dashes and wedges. That's a possibility. In fact, actually, let's stick with that because that's easier.
Are you going to go the chair?
I like that. Yeah, we'll go to the chair route in a second. Okay? If we look at, take a closer look at our hydrogen, okay, up at the top one. Where is that hydrogen? It should be dashed. Why should it be dashed?
Because the carbon is wedged.
Because our carbon is already wedged. Okay? Is that going to give us an anti-alignment? Our bromine is up and our hydrogen is down. Are those on opposite sides of that bond? Yeah. Okay? So that elimination is a possible valid one. If we go over and look at our other hydrogen, okay, we said that there were 2 there. So one of them we could draw on as a wedge, right? Oh, this is going to look really ugly. Okay, and the other one we could show as a dash. Which hydrogen would be eliminated or be part of our elimination? The dashed one, because it needs to be in that anti-alignment. The bromine is wedged. Our dash one has to be the one that's eliminated. Okay? Going the opposite direction. Yes? No? Okay, it has to be in a trans arrangement with each other if you want to look at it that way as well. Okay? What happens if we move to the other case? So in our case 1, we said our product A was an answer. Do I need to draw that product again? I'll take that as a no because I don't want to draw it. Okay? Unless you give me an answer, I'm just going to do my choice. Okay? So let's go back and now look at our bottom one. What's going to be our leaving group? The bromine's going to have to leave. In the process, we end up making that carbon slightly positive. We have to stabilize that at the exact same instant as the bromine leaves. So what do we need to do? We need to get electrons from somewhere. Where do we have electrons? And our proximal hydrogens. So, come on. We could draw on our hydrogen. Is that hydrogen drawn on accurately? It needs to be wedged. Okay? And we could draw on our other 2 hydrogens over here as our wedge and our dash. And if we weren't paying attention, we could end up with the exact same 2 products at the end. Okay? And we would say which was our favorite product. If we weren't paying attention, we'd say it's the same one, except to do that elimination, where's the hydrogen have to leave from? Has to come from the top. Is that hydrogen anti to the bromine? No. Which means, can that hydrogen be eliminated? No. Which means what ends up being our product? Whoa. We end up with the least substituted double bond. Okay? So we'd end up with something that we would refer to as the Hoffman product, but for a slightly different reason than what Hoffman first projected. Okay? So the structure forces one product over the other, which is ultimately what Hoffman was saying. Okay? We can't predict, or we can predict up to a certain point, but then the structural size is going to have an impact and change our product formation. Okay? Can everybody see those anti-alignments nice and easily? Good. You're going to listen to me again anyway. So here we go. I'm going to draw that out so we can see it a little bit better. We're going to look at the Newman projection, okay, for this guy here. Okay, well, actually, we'll look at a chair first. So if I draw out a chair, that's not a bad-looking chair. Okay, we'll pick our bromine to be wedged. So there's our bromine, axial going up. Okay, where's the methyl? It's the carbon next door. I'm going to pick that carbon to be over here. It's going straight down, which would mean it has to be the axial one, which means our hydrogen would then be equatorial coming out here. Can you see the anti-arrangement there? No. So what does that mean? Everybody's favorite, Newman projections. And we're going to look down this highlighted bond. This is the bond we're going to sight down. Okay? So when I look down that bond, I've got my carbon in back, which will be the one with the hydrogen. My bromine's in front, aiming straight up. There are the two things off to its side. If I look to that back carbon, straight down is my CH3. Okay, what's up to the right-hand side? There's my hydrogen. There's my CH2 for my ring, CH2 for the ring. What's the relationship between the bromine and the hydrogen? Not anti. Take it a step further. What is it? French gauche. Okay? Which would mean that we're not in the proper alignment. We have to shift to use the hydrogen off of the other carbon. What if we had decided to put that bromine in the equatorial position? What would that change about our structure? We made it equatorial. Our CH3 is now there. What does our Newman projection look like? Where's the bromine now? We're looking down that bond. Is it up? No. So the up will be our hydrogen. Down to the right will be our bromine. We'll have our CH2 over here, our CH2 for the ring in the back. We'll have our CH3 equatorial, and our other hydrogen aimed down. What's anti to that bromine? The ring. Would I ever be able to get the elimination? No. Okay, I can't eliminate that carbon. Okay? Kind of seeing why that position doesn't work now? Okay. Oh, now my arm's getting tired. So, substitution or elimination. So now we've got to combine everything together and start to combine our knowledge and decide which mechanism is going to occur in preference over another. Okay? So the very first thing that we'll look for, or the very first thing we can look at, would be the strength of the nucleophile and or the base. If it is a strong nucleophile or base, that's going to determine the order, be it 1 or 2. So the unimolecular style or the bimolecular. If it is a strong nucleophile, we're going to be looking at which order. Strong nucleophile means strong nucleophiles promote bimolecular reactions, which would be the two types. If it's a nucleophile, we would expect SN. If it was a strong base, what would we expect? E2. Okay? We just said nucleophiles and bases were virtually the same. So this is where this slide kind of discusses this a little bit better. We can look at our nucleophile as an electron donor and our base as a proton acceptor. A nucleophile donates its electrons to what, though? What's the big difference here? Kind of right. Cation, but particularly what kind of cation, or rather what not cation. What does the nucleophile donate its electrons towards, or to? A carbon, okay, or some other atom, okay, larger atom. So we're typically looking at donating towards a carbon atom. If we look at a Bronsted base, it's a proton acceptor, or if we looked at the electrons, it's donating its electrons towards a hydrogen. Okay, so we're looking at H plus or C plus. What's the difference between those two? Okay, you're right, it is the atoms, but what's the difference between those atoms? Size. Okay, so when we're looking at a nucleophile, we don't want a lot of size. Our nucleophiles need to have little sterics. Very, very, very small. Okay, why? Because they're going in to react with something that could be large. Okay? So we need to get them in there so that they can do what the chemistry they need to do to react with that carbon without getting pushed away. When we look at a base, okay, what's happening with our Bronsted base? We're going in to pull off a hydrogen. How big's the hydrogen? Really, really, really small, which means I don't really care how big my base is. Okay? It could be ginormous. It's just reacting with a small thing. So our primary difference between our nucleophiles and our bases comes down to size. Okay? The bigger it is, the more likely it's going to act as a base. The smaller it is, the more likely it'll act as a nucleophile. Okay? There are a few cases, in fact, there's only 2 cases where you can have a nucleophile that won't act as a base. Okay? For it to not act as a base, what would its conjugate acid need to be? It's kind of a tricky one. For it to not act as a base, what does the conjugate acid need to be? If it's weak, it wants to act as a base. It doesn't mind. Oh yeah, I'll take a hydrogen. Sure, why not? It needs to be a strong acid. Because by definition, what does a strong acid do? Completely dissociate into the ions and not react with hydrogen anymore. So if we take a look at the 2 examples that I gave up here, I minus and Br minus, which I now erased the minus there, but it's there. Barely. Okay. Because Hi and HBr are strong acids, meaning they don't want to act as bases. Okay? Good examples of bases would be things that are large. We just talked about one already, T-butoxide. Amines also act as big bases. Or good bases. We'll talk about that in chapter 10. DBN, DBU, if you want to look those up, you can, but I'm not going to draw those structures because it's not that important. They end up being very large, bulky bases. Okay? The other things that we could look to would be our substrate structure. If it's a primary halide, we really only have one choice. Okay? It has to be the SN2. Okay? Primarily. We can see some E2 eliminations in that case, but it's really, really rare. Okay? It's a lot easier to just do that substitution. Okay? If you have a secondary halide, okay, I say look to rule 1 for help. Why I say look to rule 1? Because if it's a secondary halide, you're SOL. Okay? That can be anything. E1, SN1, E2, SN2. All of them are possibilities in the secondary halide. What happens when you become a tertiary halide? It narrows things down a little bit because we can't get SN2, but then the SN1, E1, and E2 are all possibilities. Okay? Some other things that you can look for are high temperatures. How do we show high temperatures? What are triggers that you might see saying, oh, that means high temperature?
The wavy lines?
Interesting idea, yeah, wavy lines. Wavy lines could be high temperature, but that's not our standard notation. We could do the change symbol. That's an eraser. Let's try that again. You might see the delta symbol saying a change in temperature. So we're making it really, really hot. What's another option? A really obvious one. You could just say heat. Okay. Other options. Providing a temperature. 100 degrees Celsius, is that hot or cold?
It's a little on the warm side.
That's a little on the warm side. Okay, so we've probably added heat to that reaction. So there's a few different ways that you could see temperature added in there. It usually favors elimination, but it's not always an elimination result. Okay? And then bulky bases, okay, pretty much if it acts as a base only, you're going to eliminate or you're going to prevent your substitution reactions, and you're going to see elimination reactions occur. If you have a strong base, what does that mean? Which mechanism are you going to expect to see? The E2. Okay? I don't think I really have any more information on each of these slides. I went through and tried to summarize again each of these big ideas and putting them into one slide so you can see everything. So if you've got a SN1 reaction, what are you looking for in your substrate? What are you looking at as far as your nucleophile goes? Solvent effects, that kind of fun thing. So the idea is that you can see or use this information to piece out which mechanism is going to be preferred over another. Apparently, we're done. Well, no, I just turned off. So, yeah. Yeah, the very last slide is the complications. That's the summary of all the kind of primary things to be concerned about. So that is the end of Chapter 7. We will start Chapter 8 next week.